So I would like to get everyone to actually hands-on here. So that's going to be really like, I expect you to actually follow things with exercises. So if you have the time, and if you didn't do it already, you have the main event repository, but you can also go to this one alternatively if you didn't download the data set yet. But please do this and launch Docker, which was the suggested method to get the notebooks working, right? So I'll just wait everyone to raise the hand when you're ready, right? So the idea is that we're gonna launch Docker, and inside Docker we're gonna launch Pluto, and I'll show how to do that. And then after you launch Pluto, you're gonna start this specific notebook called Geodata Science-Docker. That's the simplified like one, where I hope everyone is gonna be able to follow step by step. So the way you would start Docker depends on your operating system, right? So we saw Gail explain this today, this morning. So I'm assuming that you already have the Docker launched and you are able to launch either the Julia repo or Pluto or Jupyter. And please raise your hand if you are not there yet. Is everyone ready to?
I'm not there, but I will try.
Okay.
Yeah.
Okay, just go for it. Yeah.
Is Geodata Science.jl the same as Geodata Science.jl?
So this one is heavier. If you have more powerful hardware, you can try this one, but you have Mackie visualizations. So Mackie is a bit heavier. So I did the dash Docker one is the safer one that I think everyone will just use easily. Without the Docker suffix, it's going to be heavier. So I would say start with the Docker one, and if you have later time, like later today or over the week, you try the one without dash Docker, because it has Mackie visualizations, which are heavier.
Yeah. Just as a reminder, the sessions are being recorded and are going to remain available on YouTube. So if you can't do any things now, just it's okay. You can take your time later, and sometimes it's even easier. You take your time, you go at your own pace. The notebooks are on the Git repo, ours and Julia's, and the video will be on our YouTube channel.
Perfect. Thank you, John. So I'll just continue in small steps, and I'll show some slides here while you guys are preparing so that we have something going on, right? But the idea is that you start Docker, or if you already have Julia in your machine, and especially if you have Julia 1.8, or even if you are in the bleeding edge 1.9 beta, I tested the notebooks on these two versions, so you'll be fine. But assuming that you have Docker already launched, you then go to, I don't know why it's not sharing, but let me see if I can come back to the other screen. Okay, so if you launch Docker, you will be able to press the box that has Pluto in it, and you should see this window, which is the welcome window for Pluto, right? If you're not there yet, just hang on. And after you launch Pluto, there will be this small browser here at the bottom. And this browser here will have the data sets and the notebooks that we are currently investigating, right? So if you follow the exact command I shared here with Docker, you will be able to access this folder inside the Docker image, because that's just downloading this repository, unzipping it, putting it anywhere in your machine, and then running Docker with this command should allow you to access the data sets from the Docker image. Or if you're not willing to use Docker, just launch Julia, unzip this repository, and launch Julia in that folder. It's going to be the same effect. The Docker is just to make things more smooth for everyone, right? But so, having Pluto launched, I'll just do this here. You choose the Geodata Science/Docker.jl notebook, and then you press Open or Enter in your machine. Here I would launch the normal one, because I want to launch the one that's heavier, but I think it's safe if you use the one with dash Docker. So I will just press Enter, and that's going to initialize the first notebook. That's going to be the majority of the work that you're going to do this session here. There will be a second notebook, which can be useful for you too, but it's going to be run on the Julia beta version. I think it's better. You can also run on Julia 1.8. It's fine. It's going to take more time just to load. It's very heavy. The second one has many advanced 3D examples, which will take time to load. So here you see the first notebook loading. How many of you got the notebook launching, or is it's
Not yet.
Yeah. Need to know? Yeah. So you should see this panel first, and then after 2 minutes or so, you should see the table of contents showing up here, because it's loading everything behind the scenes. I'll actually use my
But we agree that there is no notebook in the zip file you download from GitHub, right?
So there is
Geostats folder.
yeah, there's a Geostats folder.
Yeah, but there's no notebook, right?
Can I look at it? So
when
when you downloaded the repository, the repository folder has all notebooks and a data subfolder. It has everything you need, just one repository that has everything.
It's not in the, which one is it? It's not in,
In the Docker image, you mean?
no, I'm saying it's not in the hands-on sessions, it's in hands-on Geostats.
Yes, hands-on Geostats. In the repository of the event, there's a subfolder called hands-on Geostats, and everything you need is there. Let me also put timer here so that we don't lose track of time. So, initiate it. So you'll see that this will take some time to load. Let me go back to the slides so that you understand what the project is and so we get going. So what is this workshop about? This workshop will talk about two things, geodata science and geostatistical learning, which are concepts that are pretty much the equivalent of non-geospatial data science and machine learning, but in the geospatial context. And what we'll do here is like two notebooks. The first one I would like to try to follow with you guys step by step, which contains the basic ingredients that if you get familiar with these ingredients, you can do more advanced stuff by your own. And the second notebook is more for like following what is possible, showing what is possible and seeing what you can do with your own research and data sets. So short intro, I think I'll just skip this because Joan mentioned. I'm the author of this framework. I'm currently the CEO of this company, Arpeggio, and I did my PhD in geostatistics. This work has been, this geostats framework has been developed over years, and I'm really into this field. I've been doing research on this area for many, many years. And I would like to basically put the sugar for everyone that's not inside of this field to learn how to use these things correctly, let's say. When correctly here is read with double quotes, right? But you can find more information on my website. So what is Geostats.jl? Geostats.jl is a general framework for geospatial data analysis and modeling. And it's a growing scientific community. As you see, there are many publications coming out using the framework already. I will just touch some of them. And it's fully written in Julia, so if you've seen some of the efforts in the Julia community, this one is one that's purely written in Julia. We got this decision, this design decision of not depending on external libraries, and it's for maximum flexibility, right? So we want our users to become contributors and become active developers of the framework. There is a documentation and there is a forum where you can ask and interact with the community. And it's currently a very comprehensive, I would say, like software stack. There are missing ingredients still, but it's made of several packages, this framework, right? So it's a all batteries included concept. You load one package and you get everything on your session. And it's designed for people who are really interested in advanced geometric processing. So if you go to 3D geometric processing, or if you want to do more complicated geometric operations, we have this submodule called meshes, which is done in the geometric processing part. It's state-of-the-art geostatistics. It has many solvers that are not easy to implement, but it's already available there. And it also has two options for visualization, right? So there's GeostatsVis is the stack of visualization with Maki.jl, which is the more powerful interactive 3D system. And we have the old recipe system, GeostatsPlots, for the plots stack of visualization. There are other auxiliary packages to get things loaded, but these are the main submodules, let's say, for point pattern analysis, interpolation, and all kinds of things. They are in these sub-packages. Where it has been used, so it's being used by consulting groups, research institutes, companies. We've been able to use this open source stack for commercial solutions as well. So there are companies that are using, and researchers inside of companies that are using this stack. as well as smaller groups and people who are using it for consulting. Scientific publications that I think overlap with the Air Center theme. So we had people, I don't know who these are, so that's nice, right? We have a community that's made of people who are not from our circle. So these people published work on Asner and others on mapping rugosity of coral reefs. They say that the reef rugosity is a measure of complexity, of 3D complexity, that's important to monitor the impact of human activities in Hawaii, for example. They got all the islands of Hawaii and computed these rugosity maps, which are basically variograms computed on these data sets. And that was a very interesting work that I never thought of when I wrote this software at the beginning. So that was really nice. These are more recent publications of this year by people who are studying Gaussian processes and simulations of distributions in space, right? So this is work in the mining industry, this is work in material structure, and they use some of the modules for doing this analysis or visualization. That was really nice to see too. And I hope that at some point we will be interacting here more to get more publications out of the Air Center and people here, so hopefully you see your papers coming up with this tech as well. So what's the plan for today? We have an agenda that's made of these sections. This 10 minutes slides is what I'm doing right now. I'm planning to just wait you guys to get set up with the notebooks, and then we'll switch to the first session of the hands-on, which is going to be the geodata science part. Then a coffee break or something short to answer questions. I'll be available here. And then switch to a second notebook, which is heavier, but it shows a lot of the stuff that can be done already with this framework. So just to ask again before continuing, is everyone following? How many of you got the first notebook loaded and...
Can you repeat where the first notebook was located? Like once you got through
Inside the, it should be inside the GitHub, either
the Docker. If you want to try in your local machine, you have a powerful one. So if you want to try on local Julia, that would be an option too. Because you have the data downloaded already, I think that's the... You need to call download path to that file.
You should have the Docker inside there. Like, as in there's geodata science and there's geodata science there.
I think the best is to just
if you go inside of this one, this is the folder that you want to...
This one?
Yeah, so you can either load Docker and then map the folder of Docker, or you can install Julia and launch Julia from this folder. So do you want help with any of these options? Yeah, so what's the Docker looking like?
It's this one. Yes. Open this.
Should I want data in this case?
I run it one folder up actually, but that should work if you do the.
So do you have this?
Yeah, this command, what you showed, and this is just the current working directory. And I run this just JuliaEO. Check out. But you need to be able to access that folder, so that's all. You have to run that mount. So
since I'm already in the folder with this one.
Yeah, you can do the Docker run here.
So how did you start? It was through Docker?
Still the gate.
Yes, I close it and did again. I'm not sure if it's
yeah, that's what you put on the slides. That will work. It's mostly that the notebook, the Docker image has some
inside of
notebook
Pluto, you copy the path.
I have to adjust the path to the
but the notebook is
the same
Docker, right?
you need to remap the port number.
Oh yeah, is it here, right? You see the Geostatistical?
Yeah, just put a 0 for the first one.
Docker is. I have to.
Do you want to
No,
try
that's
the
one
Julia
of the
version
many
directly, or it will be
more
go
to
to
go.
the JuliaEO website?
So that should work. Will take a while. And then you click Pluto. Again, will take a while. Then you need to open.
You're going to download the binary Julia. I think we need to download it. And then you download the better one. I think you can get even better results. Like you can download this table too. Yeah. Yes. I prefer this table.
I don't know because
Yeah, you probably have
Install,
multiple
you
ones
can
for
just cd to the folder and
you already have
your
Geodata.
I just copy
No.
Or you copy
No, no, it's a repository.
I copied from
Yeah, but the
this
issues
one.
are not using notebooks, so only works
The one you have used.
Oh, yeah, so I had to.
Yeah,
This
make it
was
work.
the-
Automatically works. Just when you open this game, I will find things.
Did you make it work?
Why don't you guys try just using Pluto and then Pluto run it inside
Yeah.
directory and
Yeah,
then
it's cool.
open it?
Yeah, it was really easy.
It's just
It's probably easier to do that.
Which part is it? Did you guys
What is
see
888?
That's right.
It's the other one.
Oh, really?
I can get it.
That worked.
The
It's exactly the same thing. Already another node running out of the
Yeah. Do you like to try the alternative path with like using Julia directly on
Yeah.
your machine?
I think it's easier to use Julia directly.
Still need to install Pluto.
With Pluto, it's just one line of installations. Package add Pluto and it's down is in Julia.
Yeah.
It's very quick. I think it's saner because the Docker works when it works, but it's such a heavy hammer force just getting this to work. So if you want to go, the alternative path would be to go to the julialang.org website, download Julia 1.8 or 1.9 beta, and then install. It can be with 1.8. The last stable is 1.8. It can also do. I didn't test with 1.7, but if you want to try,
I use 1.8. 1.8 works.
yeah. You got it running.
I got it running.
Nice.
I haven't tried the one on stats though. So.
Yeah. So just for the sake of time, let's say, let's see how it's going here. Installing still.
I didn't use Docker.
You didn't use it?
I didn't use Docker. I think it's just easier to do it without Docker because eventually people are not going to use Docker.
Yes.
Okay, so I noticed that my problem is the folder. I have to change my
To the
directory.
folder, yes.
So that's the problem I'm
See if I
having.
can just do
I don't
Yeah, so-
know, because I changed the directory to those folder.
Yes.
Okay, but then when I run your program, it's not, it doesn't work.
If it's the same.
Oh, yeah, like you said, it will take a while. I'm not sure what
Because I
the.
ran this control from Linux and Windows, and I'm also using PowerShell. And the exact same code works.
Yeah.
Docker, so everyone can.
Using Pluto.
So it's the.
It doesn't make.
But wasn't the so I have Docker wasn't supposed to be in the
I have the same problem, yeah.
Well, I have to prepare something for Thursday. I just refresh. Probably.
It's just typing this full path. So you replace.
Oh, by the way, I'm Mark. What are you
So
presenting tomorrow?
It will launch on
They show looks into our
it will
software.
launch in the browser, you get some gadgets.
Oh, cool.
So just
And then
Together with Felix.
go to
no, actually he's
this one.
before. He's not like this is more open and better science.
Yeah.
Sorry. Erase this dot.
Geoscience.
Oh my goodness, that's the
Change
erase
the text and
this
stuff.
first dot. This is just to indicate that this is running on terminal. I should.
This is why Docker just creates more box
I
blocks.
was running on the terminal.
Program language, getting it,
Did you got it?
So you have to.
Okay, we try to do all
Yeah,
that.
but then
You'll have
you
raw-
have to put
raw
the
source
same
data.
thing.
What it's,
I didn't
working on.
Yeah,
Yes,
but
at the dollar you
Yeah.
can go back to
It is
this
next to
command.
What's your use case?
If I don't have the first dollar, and you are in the right folder.
I'm working on
No, 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 because to
Yeah,
create
they are not
the
the
way
way
you
done.
do
Yeah.
it.
The way
Yeah.
it's
But
let's
I'm
say
working
it's-
with
So
maritime.
just
But
remember to draw it.
Okay.
Yeah, me too. It doesn't
Are you?
work.
Oh, this is coming from.
But honestly,
Do you have
it's just
PowerShell?
the side project for us for fun.
Yeah.
Yeah, but
Yeah, just
I have to
Yeah.
go.
The dot is
How about you?
at the beginning.
So we
I'm
should
presenting
do-
Yes, so the Julia.
I think
So
it's
this-
Oh my goodness.
on what? I'm not sure if it's on the website yet because we changed the name of the talk. Because the first was estimating reservoir storage. But we decided not to do that because I'm not an expert on that at all. So I'm now doing innovation modeling. Point clouds, LiDAR.
Yes, Geodata and storage.
Processing LiDAR and showcasing the backlights that are available in
Maybe we should add some innovation on SAR.
Well, SAR is definitely, especially in SAR, of course.
We are going to showcase SAR.
Oh, okay.
And it's not
launch.
Wait, you're gonna do the whole in-SAR pipeline yourself in Julia natively?
Yes.
Wow.
Well, so far we have it where
Difficult, right?
it's hacked, so it works with one image and another image.
Sorry.
Goes to
Everyone goes there. It's possible to not.
but it doesn't work like
Like interferogram,
There's
unwrapping,
a
all
lot of,
that other stuff.
there's a lot of it's just just the
And
open
then
file.
let's continue here this session. And so after it's
No weird
installed, you can just say using Pluto,
Have a look because
Just
it's
Pluto.rem.
Okay.
and then you can choose.
Same line.
Open the image, open it.
And then enter, and then the second line will do it.
Oh,
Yeah,
I'm
yeah.
actually now going to pull request just it's my actual version, just for your reason, just for Tuesday, so it's way easier than it is now. Because there's like the last file, that's just one cloud dataset file, essentially. It has two skills to work with data. So the coordinates are like integers, and you have to scale them to flow through cell scaling and offset. So I'm trying to prevent all of that and make it as easy as possible.
It works good.
It doesn't exist yet. So I've got some days left.
Don't worry, you have some data. I'll just more. We haven't finished our
Sounds very familiar. And looking at it actually, I think we will spend most time just getting the installation to work.
Yeah, just add
Right, because we haven't talked about use, that's all.
I'll mention
Do you have the original command from the, we can just copy.
Yeah, will you have notebooks and all that? Or is it just
no notebooks, but you don't
From
have
the
downloads.
Oh.
You just have some file.
Yeah, so people could run it in Docker if they don't have
Sure,
Julia
this
set
is the
up.
folder with everything, right?
Yeah.
You can choose to
Yeah,
just as
map
here.
the folder, just that folder instead of the one. Now is the prompt. If you have PowerShell, the other, you can type PowerShell, this is the PowerShell.
The styling and everything.
Yes.
Yeah.
This is
So CD download, CD space.
Wat daar van buiten.
Yeah, sometimes I disagree. But I cannot really make very nice stuff.
Oh, but now CD is the folder of the tab, it completes, like, you say, Julia, right? Yeah, that's it, right? That's main one. That's okay. That's what you asked to see.
I think it's like you're running.
So now we're in the now we can copy this Docker command from the back.
This one, it basically just all the numbers into token definition.
Just this.
From the D.
What's it called?
Windows prompt is really problematic. See if it goes.
That's why I have
Yeah, you work using Pluto.
If you just
Also,
change
a
different
Pluto
words,
run,
man,
but
the Docker is so
very
difficult.
cool.
Can we want to try the directly with Julia install instead of in the Docker? It should be easy to install.
I think it's
Ja, dat is het voor X.
Yeah.
Just copy it. Okay, so I have to open it. Yeah, Mas mesmo quando aparece o erro, não aparece
Isso é
outra
muito
coisa.
like tem que ser no Windows PowerShell.
Não pode ser aqui.
Eu estava no comando pronto e deu
Yeah. Pluto. And now you choose the notebook and see if it works. Yeah, I mean, hands-on has to be hands-on. Like, although it's like annoying to get from one to go, but I think it's better to have it than you guys
for sure.
Am I the latest one?
I don't know, maybe you guys got something working already?
It's
Yeah.
still
Yeah.
loading.
Shut the notebooks.
Geodata Science-Docker.
This one?
Yeah. You are with Julia locally, right?
Yeah.
Nice. 1.7 or 1.8?
This is 1.7.
7 or if it's going to give you issues, right? But I tested on 1.8 and it works.
Yeah.
So let me get back to the agenda then.
So it's using Pluto and then
Pluto.run,
right.
open parentheses, close parentheses, and this is one command using Pluto.
You got the target.
Sorry.
No, you just fine.
Okay.
It's still going. No, you can type. I think it will show up at some point. Yeah. So let's see if things are still working as expected. So I'm assuming that most of you got the notebook launched. We can stop again to see this, but let me restart the timer. And let's go with this first session of the hands-on, right? So this module here. Hey guys, let's start the first session. Let's see. Everyone is with the notebook loaded already? Cool. Yeah, you're still waiting, right? So in this first notebook here, what we'll do is cover the basics of how you load, let's say, how do you represent geospatial data in this framework and how you do processing. So basically how you create data pipelines to take one geospatial data set and convert into another, right? So the main objectives of this section are to introduce these fundamental concepts of geospatial data. And when I say here, learn the right way, I mean, take it, like, interpret the way you want. Like, what I mean is, I've been developing this package over years, and I think I got a way that's kind of proficient to work. Like, so if you follow these simple recipes, I guess you can get very complicated pipelines quickly with your geospatial data sets. And then to practice some of these tools, right? And then we will see how this can easily escalate to something very complex. So you can build very complicated pipelines if you learn these basics here. So what is geospatial data set? Geospatial data, so in our framework, we understand geospatial data by the combination of two things. There's this abstraction of a table, which is something that looks like a table, right? So you feel that there's columns that are named, which represent variables in your problem, and there is a geospatial domain. So these two together, they form what we call a geospatial data set, and strictly speaking, this is a discrete data set. So we have a discretization of a geospatial domain, right? So we have a mesh, a grid of cells, or a point set. These are like enumerable set of geometries. So you have first, second, third, and the nth geometry. This is the domain, plus a table with n rows. And so the way we abstract this out is by this single function, is the function georef, which takes a table and a domain and constructs a geospatial data set, right? So this function goes one way, where you take any table, say a CSV file or a raster array that Raf showed in the presentation there. It's also a table as he presented, and then you map it to a domain. The domain has many types of domains which are coming from the mesh.jl package, and then you can do the other way as well, which is given a geospatial data set, you can recover the table and the domain using the functions values and domain, right? So the basic example here is, for example, assume that you have a data frame, which is just like a data set with two variables, A and B, and you would like to map this data frame into a geospatial system, right? So you can, for example, do georef the table on a set of random points for example. That would be one possibility, right? Where you can now see that there are two variables A and B, and there's a special column that's always going to be called geometry, which contains the points or the quadrangles or the triangles or any kind of sophisticated geometry that you encounter in GIS solutions, right? So here's a simple example where we map these two variables to a random set of points. But you could also map this to any set of geometry. You'll see more of that in the following sections here, right? So, for example, if I map this table to this random set of points, I get a point data set that I'm saving this variable point data. And one of the things that we're building here is to hiding a lot of the complexity on how do you plot and how do you process this and interpret this data as if it was a table, right? Although it's not a table, you can, for example, feed this point data into, I'm calling here in my notebook a viewer, but in your notebook, if you loaded the -docker1, it's going to be a plot command, and the plot will show the data with the plots.jl stack, and the viewer will show the data with the mackie.jl stack, right? So this viewer here for me is interactive. For you, it's not, right? But you can load, you have this access to the other notebook as well. So you can zoom in, zoom out, and you can see this menu here at the top, which will show you all the variables of this data set so that you can quickly navigate your geospatial data set. The idea is that this viewer will be improved over years, and the viewer itself is trying to do some smart things here, like choosing the color scheme for you depending on the nature of the variable. It's trying to automate some of the things that you usually have to do anyways, right?
Can you zoom in a bit? I think it's also good for the video.
Zoom the full notebook?
Yeah.
Yeah. I mean,
So much white space.
cool. What about now? So now that we have this data loaded, right? So we can do the same, but let's say I want to reference it to a raster, let's say to a grid, whatever name you use to represent a grid of cells or geometries. That's the same thing. You use the same georef command where you have a set of variables and you map it to, say, a Cartesian grid, right? So I'm saying there are 10 by 10 cells, which are, when you say here like this, you can actually get instant documentation by pressing the live docs here at the right bottom, and it will show you how to construct the Cartesian grid, right? So there are many types of constructors, and the one I use here is just saying, okay, it's a 10 by 10, I don't know where the origin is, where the spacing is, but there are many ways you can construct the grid. And the way you construct the table is also very flexible, right? So in Julia, although I'm using the data frame here, you can, in Julia, all valid tables are, for example, A equals run 10, B equals run 10. This is also a table. So a tuple of, a named tuple of, sorry, an extra parenthesis. A named tuple of vectors is a table. Sorry, I missed one parenthesis here. A named tuple of vector is a table. Also, a vector of named tuples is a table, right? So if I say A equals 1, B equals 2, and then another tuple, A equals 2, B equals 3, these are two valid built-in table types in Julia. So you don't need to load any extra package. If you use a vector of named tuple or a named tuple of vectors, these are tables. And if you want to use a more custom type of table, a data frame or a raster type or any type that implements the tables interface, you can. But after you have this georeference to a grid, you see that whenever I try to send this data set to the viewer, the visualization will automatically detect that this is a Cartesian grid, right? So you can still zoom in, zoom out on this geospatial data set and see the variables in the feature table, right? So the idea here is that we'll be able to quickly operate on different kinds of domains, but agnostic to the type of the domain. So you can load point sets, domains, grids, whatever. The pipeline will be the same. Now that we know how to do this, I would like to ask you to do a little simple exercise, which will just get you with the hands dirty, right? So here I'm just, before we go to this exercise, I'm just showing that you can take this geospatial data set and call the values function to retrieve the original table, or the domain function to retrieve the underlying domain, right? So you see that when I did the point data here at the top, I georeference the point data to a set of random points, right? It was a vector of points, but if I do the call here at the bottom, just so that you see, and if I say the domain of my point data, it will show a point set, which is a set of random points that's wrapped on this domain, the point set, and it knows that this is a set of points that has specific behaviors, not just a vector of points, it's a domain, right? Now the first exercise here is this Boni data set. So I'm bringing data that is coming from the industries I'm interacting the most, right? But you can imagine that this is a data set from climate, agriculture, whatever field you are working on. And this data set here specifically comes as a CSV file. So this is the Boni data set. It's from this group here in this copyright notice, right? And this data set basically has a bunch of mineral grades, which is basically saying it's a 3D subsurface model which has cells that are hexahedrons, and each hexahedron represents a volume of rock with a given grade, which is like percentage of a mineral. Say, here I have that much percentage of gold, that much percentage of copper, that much percentage. So these are just variables that I'm seeing here in parts per million. Gold, Ag, copper, arsenic, and so on. And there are other variables here that are the type of the rock, for example, the lithology type we call, and the oxidation of the rock. These are just specific to the problem, right? But the idea with this data set is that you basically get the georef function and understand what's happening. So if you go to the georef documentation, what I'm asking in this exercise here is that you just georeference this table using the east, north, and RL columns of the table, right? So if you see this data set was already loaded, that's super basic, just make sure that you are running the notebook along with me. So I'll give it like 1 minute. If you are like already doing it, or if you're already done, just raise your hand.
I don't know, but like we have a little bit issue with the dependencies.
Yeah.
We got the notebooks started, but it's not showing any. Oh, look, mine is showing something now. I take it back.
I don't have no.
It's you know the background. When the speaker comes and looks, it works.
It's called Moore's Law.
Yeah.
You should look here. So
No, it's still.
I don't know.
Yeah,
I
the
started
very
again.
beginning, that's like, what's the
then it worked.
configuration of your
So it was like
laptop? Is
a
it
emotional
i5? Oh, you mentioned that. It should be fine. Mine is a tablet and it's like very low end. That it's not powerful, right? I don't know why it's not. The blocker is really adding a layer of. Do you have many apps open at the same time, or is it just? Wow. No, because your machine is supposed to be more powerful than mine, I guess. I definitely chose to use the tablet just thinking of the low end, right? So if it works on mine, it should work on most machines. Can you do, if you want to try the alternative path of running Julia locally, of running Julia directly on your machine, so you go to, do you think it's an option? Yeah, that's the official website. And then you download 1.8, or if you want even like bleeding edge 1.9, which is the one that's going to be released soon. Right, so Windows, you can choose 64-bit. Yeah. And then if you install, I think Alex can help you with things.
Thank you, thank you.
Yeah, so assuming that you guys did, it should be super simple, right? But I'll do the answer here so that we don't waste too much time. It's a minute already. So the answer is to replace this missing here with the solution, right? So the solution is simply georef my CSV onto these columns, right? So there is east, north, and RL columns, which are the coordinates of this data set. So you say east, then north, then RL, and that's just specifying a tuple of columns which contain the coordinates. And if you just hit Shift Enter, you'll see that the answer is the right one, right? So this should turn green for you. So the result of this georef operation on the table, as you see, it's repeating the same table, but at the end you'll see a special column here again, the geometry column, which just took the 3 columns, the east, north, and RL, and created this point type, which is just representing the location as a point, right? The nice thing about this object, this geospatial data set type of object, is that it behaves like a data frame, right? So if you are familiar with pandas, or in the case of Julia, data frames.jl, you can access the rows and columns as if it was a table, but it does some smart things behind the scenes, right? So if you say, give me the first to the third row, which are samples, and give me all variables, right, as the columns. So it returns here this subtable, where you have this quadrangle geometries, as you see. So I'm showing here the example with grid data, right? So I got my grid data set, which was georeferenced to a grid. And if I say 1 to 3, it just extracts 3 quadrangle geometries from the data set. If I say grid data, give me the first row or first cell of the grid, it returns this tuple, which has 2 features, A and B, and the geometry as a quadrangle, which is a Julia object that has many functions defined. If you say, give me all the rows and the variable A, it's going to return the column as a vector of numbers, right? And if you do this special column geometry, it's going to return the domain. That's a special difference here. So because the Cartesian grid is a lazy object, right, it doesn't store any memory, it knows that if you access the geometry column, it's actually giving you back the domain as a lazy object. It's not creating a set of quadrangles. If your grid is your raster is very big, it's just going to return the configuration of the raster. Where's the beginning, where's the end, what's the spacing, and so on, right? And after we have this basic manipulation, which is, okay, I know how to georeference tables into domains, and now I want to do some processing. We go to the idea of geospatial transforms to create these pipelines, and that's where things start to get more advanced, right? So if you know what this idea of pipeline is, it's pretty, let's say, short way of representing data transformations in sequence or in parallel, right? So here is, we call this pipelines from the submodule called table transforms.jl, and there are a couple of pipelines transforms defined, but here, just so that you understand what's going on, the way you create pipelines is by designing specific transforms, pulling specific transforms from this list of transforms, and concatenating them with this operator called to, right? So if you go to LaTeX, you press \2, and then press tab, it converts into the arrow. And this arrow is just saying, take a transformation and make it another transformation in sequence, right? So when you stack these two, it creates what we call a sequential transform or a sequential pipeline, which is independent of the data set you have at your disposal. And then after you have this pipeline defined, you can apply the pipeline to any geospatial data set. If the domain is point set, if it's a grid, if it's a mesh, it will work the same, right? So you, for example, here I georeference the CSV to this raw variable, let's say the raw data set we loaded, and then I can take my raw data set and feed into the pipeline with this operator. This is a generic Julia operator to just feed input into a function, right? So what I mean here is that this pipe object, which is this pipe that I'm defining here, you can call it as a function like this, and that's going to be the same thing that I'm doing above, or you can just say feed this into the function. That's a Julia syntax to say feed my variable into the next thing, right? So that's the native Julia way of writing pipelines. So, but notice the difference. Like first we create the pipeline with the to operator, which is just constructing new pipelines, and applying the pipeline is this different operator, right? So that allows you to create pipelines that are lazy. So you concatenate many transformations, and then only at the end you just apply it to the data set you have. So building pipelines, right? So this is a sequence of small exercise so that you get used with the syntax again. So there is this web page here which you can click and you go to the list of pipe transforms defined. And then the exercise is to basically create the pipe 1 here, which replaces all missing values by the value 0, and then coerces the types of the variables geo and lito to be a multi-class variable. So I will follow this with you, but the idea is that you go to the documentation here and find out which are the 2 transforms that represent these 2 actions, and write the pipeline here. Replace the identity transform by something more complicated. So, still have time. Let me see here. Did you manage to get this one working? Using Pluto Run.
Depois que eu tenho a opção para aparecer os ficheiros, não sei porque não aparecem os JS.
Ah, eu acho que deve ser a pasta que você rodou, mas você pode, antes de fazer o Pluto Run, já foi,
Sim.
sem problema.
Depois. Ah, ok.
Porque é só você mudar de pasta, mas aí a gente consegue fazer do mesmo jeito.
Porque a pasta é essa, aparece esta, mas não aparecem os...
Clica num desses arquivos aí qualquer, num dos notebooks. Hands-on Geostat. Pode ser essa pasta também, acho que vai ser o mesmo material.
É isso, não é?
Isso.
Esse que aparece.
Isso. Aí clica no Docker, no de baixo, esse. Aí só copia o caminho completo do arquivo e coloca lá no Pluto que ele vai funcionar, eu acho.
Ah, ok.
Lá no seu navegador de arquivos.
Pois.
Aí vai lá naquele arquivo, no browser mesmo que você estava, no navegador de arquivos. E aí... Isso. Aí copia o caminho completo para esse arquivo. Ctrl C. Coloca lá no Pluto. E aí, barra, tem que ser o caminho para o arquivo, né? Aperta Tab para ver se ele vai. Não, acho que você fez alguma coisa, abriu outro. Não sei o que aconteceu.
Pois, estão dois embora.
Copia outro.
Ele aparece aqui, às vezes.
Copia aquele caminho. Agora aperta Tab. Ele não está mostrando o arquivo, que coisa. Qual é o barra? Ah, tá aí.
Pois.
Aí clica.
É isso. Agora apareceu.
Okay. Aí o Docker.
O Docker, ok.
Aí Enter.
Ok.
Oh, I think
Okay.
now it goes. Let's see. Conseguiram fazer o que?
Isso.
Sim?
What do you mean by coerce?
Coerce, the type, is to change the scientific type from continuous to categorical, so multi-class. So if you look at the hint here, coerce is the transform we want. So it has the docs you need. So if you type coerce in live docs, you see what it does exactly. So yeah, it uses the scientific types of GL to represent the data as if it was multi-class, right? Because by default, when you load like floats, integers, and stuff, it's not categorical.
Yeah.
So it's gonna just use categorical arrays to convert things. So let's see how you still didn't get it here.
It crashes something.
The Docker one?
Yes.
Can you try it again? Yeah, that's right. It's difficult to make it work in all hardware, but it should work. Most of the people there got it already. And so you said it crashed when you're trying to do the thing, or it didn't even load?
It loaded, but I think it disconnected.
Is this the Docker one? Or is it local Julia? Because I think people there had to try local Julia because Docker was too slow or something like that. I use the Docker one. If you want to try, I mean, Rafaela and other people there, they installed Julia. He also got it directly, like installed Julia locally and launched directly on the machine instead of running Docker and then inside Docker running Julia, right? So if you want to try it, you go to julialang.org, download Julia 1.8 or 1.9, and I can come back here again to give you. Basically, you install it first, and then you say to me when it's ready. Come in.
How do you do two actions at the same time?
How do you concatenate two transforms?
Yeah.
\2, \to, and tab. It creates that arrow operator.
Ah, yeah.
So I'll just do it here so that you see. So the first transform is replacing missing values, right? So there's this operation in data science called coalesce, or in stats and machine learning, right? So you say coalesce. This is the transform, and if you open the live docs here, you see that it asks for what's the value that you want to replace the missing by, right? So you say replace missing values from the table with this value. You can also specify specific columns or a regular expression to choose columns to do this operation, right? But here's, for example, coalesce with the value 0. So I would say coalesce with the value equals to 0, and it creates my first step of the transform of the pipeline. And now the second thing I want to do is to change the scientific type of the columns geo and litho to categorical or multi-class, right? So you say \2, and then you say coerce, and then you can see here that the notation is give me a set of pairs for doing the conversion, right? So it gives examples here at the bottom. So coerce the column 1 to be continuous, and the column 2 to be a count variable, and the column 3 to be something else, right? So what I'll do here is coerce the geo column to be multi-class, and the litho column to be multi-class, right? That's what the exercise was asking. And so if you create this pipe 1, it will be a sequential transform with coalesce and then coerce, right?
I have a question.
Yeah.
So if you do the replace in the start, you will get this exact same result.
So if you do
the replace transform.
yeah,
Okay.
you can also replace missing by something else, right?
Okay.
Yeah, I think that would be an alternative. But the advantage of coalesce is that it's also changing the resulting column type. When you do replace, the column type will still be a union of missing and int.
Ah, yeah, okay.
The coalesce will change to be actually a column of int. Say it replaces, to make sure that there's no missing value, it's actually going to change the type of the column to something more specific.
Julia, I don't know if it's possible to zoom it a little bit more.
Here as well?
Yes,
Yeah.
please.
One more? One more? Or it's fine?
Yeah, it's fine. Thank you.
No problem. So that should be big. So the second exercise here is to do this other sequence of actions here, right? So I want to select the variables gold, Ag, copper, arsenic, and sulfur, and then I want to perform principal component analysis, which is this multivariate statistical
I
transformation.
just have a question about the coerce.
Mhm.
So does it call the multi-class on every element of the table? Is this
So you choose the columns that you want to change the scientific type, right? So example, convert the column geo to multi-class. It will take the column, will look at all possible categories, the classes, and it will create a categorical array with these 3 classes. And so if there are like many repetitions of class 1, class 2, it will just create the categorical array which stores the 3 classes and repeats the number of entries.
safe memory? So
Yeah. And also it encodes explicitly that this is a categorical variable, so that when you do a classification problem or clustering or something, you know already that this is categorical. It behaves like a categorical variable.
Okay.
So in the second one, the idea is to select and perform PCA, right? And the good thing about this table transform submodule is that it allows you to do these very complicated transforms, which are not just pixel-wise or I would say like row-by-row operations or column-by-column. Right? So PCA is a multivariate transform. It takes many columns at the same time. It produces many columns. it's, let's say it's a more sophisticated transform that works here in any geospatial domain. So if you have a raster, or if you have a point set, or if you have a mesh, it will do PCA on the features wherever you are, right? So, well, I'll do this here live as well, because I know you are still working on this, and then I'll pass again on the table to see who is having trouble, right? So the first action or transform here is the select transform, which is basically a fancy way of selecting features or columns, right? So if you look at the live docs, you see that there are many ways to specify columns. We call this the call spec. And you can say, you can pass strings as the names of the columns, symbols, regular expressions, and it will understand that you want to select this column, right? So the way I'll do here, because I know that my data set that I loaded here at the beginning, it's called raw, right? My raw data set has these columns as the first 5 columns. I'll just use the syntax 1 through 5 instead of typing everything, but you are also allowed to do anything, right? So say, give me the columns 1 to 5, right? That's one way of specifying this transform, right? But you can also do explicit lists, right? So you can say column AU followed by column AG followed by blah, blah, blah. That's another way of specifying the same transform. But for short, I'll just say 1 to 5. Now the second transform we want to perform is PCA, and there is a PCA transform, so I'll say backslash to PCA. And if you open the PCA documentation, it's going to give you what are the options for PCA. You can say that's the maximum number of dimensions to retain, the ratio of the variance to retain, right? So this is detail of the implementation, right? So the PCA transform is implemented as a sequence of 2 transforms. First it computes the z-score, and then it gives the eigenanalysis of this v-basis, which is one specific way of projecting the PCA transform. And then it has, for example, it's equivalent to this, right? So when I'm typing PCA here, what happens behind the scenes is actually taking this transform and adding to the pipeline, right? So I'll say, compute the PCA of this. I'll not specify any option, just PCA as this. And you see that the pipeline that was created actually is select, followed by z-score, followed by eigenanalysis, right? And that's doing the workflow bit by bit. And after you have this pipe 2, the pipe 3 here is to select the density variable, which is this whole row variable, and then compute the z-score. So I'll just do this here live as well. So I'll select the variable row with this column, right? So that's the variable. And then I will feed that selection into the z-score transform. An alternative way to write this would be just to use, I think that's the version already that's loaded, z-score of the column row. So some of these transforms, they already accept the column specification, so you can just skip the selection, right? It's the same thing, so it's going to apply the z-score transformation on the column row. And so, see, I'm building my pipeline without even talking about the data set, right? Everything is separated so that you can build it once and apply it to multiple data sets, right? And then the last one here, so that we get things working, that's going to be a geospatial one, because so far, all these transforms were applied to the features, right? To the covariates of the problem, the columns, A, B, mineral grades, and so on. We also have transforms that are applied to the geometries. Say, I want to standardize the coordinates to live in a box -1 to 1, or I want to rotate my domain, or I want to translate my data set to somewhere else. These are geospatial, and the good thing about this pipeline is that it combines both feature transforms with geometric transforms smoothly. So you can create pipelines that combine the two, and all the magic will happen behind the scene. It will be transforming the domain, transforming the features, combining things in the end, right? So here I'll say standardize the coordinates of my domain. So if I look at the docs, it's always nice to see if there's options. So there's no options because standardize is what it does. And then I'll follow that to another transform, which is dtrend. And dtrend is a covariate transform. It's a feature transform, but it uses the coordinates. So it's feeding a polynomial to the data set to identify some trend, and then it's removing the trend from the data set, right? So say I have a map where the temperature is increasing in the north-south direction. I want to remove this trend. I create this d-trend transform so that it removes it out from my data set, right? So I can specify the degree of the polynomial. So I'll say degree equals 1, but it's the default, right? And it creates my pipe 4 pipeline. After that, I can combine all of this, which is already done here. So you see, I created sub-pieces of my final pipeline. So I say pipe 1 followed by pipe 2, and then this operator here is this one, \sq cup, which is basically taking the result of 2 pipelines and concatenating horizontally. So it creates, imagine that you generate one table with one pipeline, one table with another, and they're all in the same domain. You can just concatenate the features with this \sq cup, which is disjoint union, right? So you say apply pipe 1, apply pipe 2, join with the pipe 3 followed by pipe 4. And I think I missed something here because the result shouldn't be an error, right? So let's see if I missed some of the pipelines there. Let's see what I did. Pipe 0 was coalesce followed by coerce. That should be okay. Multi-class, right? Then pipe 2 was select 1 through 5 PCA. Then pipe 3 was Z-score. And then pipe 4 was STD coordinates followed by D-trend. It should be okay. I don't know why we get this error. Maybe I missed something. Yeah, it's very difficult to read error here. Let's see if I can debug like apply D-trend. There was an error in the D-trend operation for some reason. Oh, I didn't specify what column to D-trend, right? So it's asking to D-trend all variables. No, it should be okay with degree 1. Let's see what's the data set looking like. It's weird because I thought it was working with all columns. So let me just choose column 1, AU here, to see if it works now.
It works for me.
It works for me too.
It works for you, right? What did I do differently? I mean, the instructor got it wrong. What is the what's the thing? It worked for you guys. You got the same?
But did you run the one where you combine all the pipelines? Did you run the line where you combine?
The one will automatically run.
Yeah, everything's synced, supposedly. For some reason, I'm not getting... Oh, it's running again now. Oh, I think it was actually stuck. My Pluto was outdated. I think it should be... No, it's still not running for me. It has to do with the categorical array. So let me just see if I did the... I specified the name of the columns. Maybe I have a typo. Geo multiclass and Lito multiclass. Yeah, I don't know why it's not doing the thing.
It's just hard to keep up with thing and everything works at once.
Yeah, if it works for you guys, I don't know why it's not here. I think I have something like super basic that I'm not seeing, but it should work fine for you, right? I don't know what's happening for me. It's trying to use categorical values where it shouldn't be using. Yeah, so nice that it works for you guys. So this was just to show that you can easily construct pipelines, right? So you can take these small transforms and build very complicated pipelines at the end. So before we go to the next section, I will just show these examples here. So these are other examples of pipelines that can be used. So for example, take my data set and feed into these 2 transforms, right? The first one, you convert the lithology column to a multiclass, and then after it's multiclass, you do one hot transformation to break this lithology column into 4 columns, as you see here, where each column is a binary of 0s and 1s. So for example, say you have a categorical variables that you want to break into multiple maps of 0s and 1s. That's called the one hot transform. It's very common in machine learning when you're doing neural net stuff. You break the categories into maps of 0s and 1s, and you train the net on these more low-level 0s and 1s, which are indicator maps, right? Notice one thing that I would like to emphasize here with this session is that these are very, let's say, handcrafted operations because they know the geospatial domain behind the scenes, so they avoid creating copies of geometry. So it always tries to make views and subsets of the original data set to avoid copies, right? So if you say, for example, filter my data set where the gold is above 0.5 and the copper is above 0, and if you ask for the domain of this new geospatial data set, it's going to be a view, right? So it's just filtering the rows, finding the indices where these things hold, or where this filter is valid, and then you do a view. There are other operations like sampling as well. So sampling is also just taking subsets of the original data set, so it's also going to be a view. And you can do all sorts of things. One of the very important, let's say, features of this pipeline approach here is that they are revertible. Meaning that if you create a pipeline, you can undo all these operations in sequence to your final result. So for example, this is very common when you need to do statistical modeling on Gaussian or normal distributions and your distribution is not Gaussian. You do a pipeline to get to ideal state, so you transform everything to Gaussian, you standardize the coordinates, you do everything there, perform your modeling, and then you want to come back to the original space. So you undo the operations, the full pipeline. And that's very easy to do because you can just say, create my pipeline P, and then you use this other operation here. So it's instead of applying it as a function, you say, apply my pipeline to the data, and it creates the new data set, which is the same thing as applying it as a function, but it also gives you this cache variable, which is a generic way of saying, this is all the information I need to undo everything, right? And so this cache variable here is complicated as it gets. If your pipeline is complicated, this cache will be super complicated, but it doesn't matter. It's just a variable that you store somewhere, and then you can revert later. So you can revert your pipeline with your new data using the cache, and then it gets back to the original feature space. That's super important for statistical modeling because some models require you to be between -1 and 1 or Gaussian distributions, and so you need to map there, work, and come back with easy, right? So before we jump to the final section of this first notebook, I'll just go over the table again to see if there's any issues or anything that I can help.
In the documentation, there's no PCA or some of the higher level functions that combine, for example, Z-score and...
Interesting. So it's not showing up in the Geostats docs, you mean?
No, it's not.
So this, as you see the docs there, they show the code that generates the exact set of transforms because they come. Some of them come from the package table transforms.jl, right? So if I click here and I open the transform,
it comes up in the Pluto documentation, but in the documentation
oh yeah, I know why.
It's not there.
It's because the PCA, as I showed in the docs, is just a shortcut for eigenanalysis, right? Z-score followed by eigenanalysis. So I think the way that we print this hierarchy here with abstract trees, it's not taking the aliases, right? It's just showing the eigenanalysis here and the Z-score separately.
I see.
So,
but some people, i.e. me, will not know that.
Yeah. So the idea is that these transforms come from this package here, table transforms. Right? So if you go to table transforms docs, there will be the full list of the transforms that are the feature transforms. So table transforms, it stores the transforms that are only on the features, right? On the feature space, the columns that represent variables. And you can have the full list of transforms in this documentation. You see that the PCA should show up somewhere here.
Yeah, it does.
Yeah.
Okay, that one does.
And if it's not on this table transforms, it means that it's somewhere else in the stack, probably on meshes, because it's a geometric transform, or parts of it are also in geostats base, which takes these two words and combines with specializations, right? So there are some specializations we need to do to avoid copying geometries and all these things that happen in other packages, but the idea is that geometric transforms lives in meshes, feature transforms lives in table transforms, and sometimes we need to do some specific things to dispatch them together. And so let me go back again to the round table to see if there's anything. And then we will go to this last session, which I think is super powerful too for data science, which is one of the things. Did you manage to?
No, still running.
Oh,
Seems.
wow.
All of them.
I'm impressed because I was telling people I have a tablet, right? Again, it's working. It's Should be faster in yours than in mine. I don't know why.
Like the advantage you have.
Is it Docker is still running, or maybe if you close all the apps that are like consuming your memory or something like that?
I guess so. I should just restart this machine.
Yeah, I don't know how many apps are like. If it's super heavy on the other apps, maybe it's. Yeah, it was installing stuff there.
That's almost like you want
Yep.
Well, I just want, because in pipe 1, what we did was we converted geo and little to multi-class, but in pipe 2, what we did was we didn't select those two classes. So in the end, in the data that in the resultant data that you find, it doesn't include geo and little in that part of the analysis. So is that part of pipe 1 actually necessary?
No, yeah, I created like a dummy example.
Okay,
Like, yeah, just combining things. But yeah, if you expected to see the geo and little there, yeah, I didn't add. But you can actually take the final pipeline and put a SQ cup, follow up with a selection of geo and little, and you should add the columns back again, right?
I see.
But yeah, that's a good question. It's basically like the example is not like it's looking like it's discarding parts of the pipeline.
Yeah.
Right? Yeah. It's just like an example. Yeah. Tá. Deu certo, né?
Sim.
Maravilha. É um desafio mesmo para fazer funcionar. See and go to the other side. Yeah. So if you launch Pluto there, like what happens? And Docker is really, I don't know, anyone got it through Docker? Just asking.
Yeah, it takes a long time.
Yeah, Docker is just, yeah, you can try, but I think my impression that many people switch to just installing Julia locally. But if you select the app down here, yeah, so click on this, and then press that. Just that, and then the Docker one, press enter. And I think Pluto has this button that you click on open and it just erases the tab. Great, it's weird, yeah. On Windows only, by the way. In Linux it works. If you press open, it works. What about you got the install, right? So you say using space pkg with capital P, yeah, and then pkg.add, open parentheses, and then Pluto, double quotes Pluto, double quotes, Pluto, yeah. And then you install Pluto, and then you can say using Pluto, Pluto.run. It will launch Pluto locally instead of in the Docker. Using this Pluto.run. Yeah. Very explicit.
Yeah.
But it's not just plot, it's
I'm having the
so they
same
call it
error
first
that
time
you had.
text.
Yeah.
But I don't know why.
And I don't know, maybe I got, yeah, maybe I got some of the transforms incorrectly. I don't know why. It's
It takes a long time to load the package, because it compiles.
yeah, let's review it slowly, right? So see,
Yeah.
Yeah, when it's done first time, it's still very
This
fast,
is
because
one.
everything is fast.
Yeah.
This is
So
all.
in the version that needs to allows you
I
to
think it's called.
Yeah.
Yeah.
Then the second one,
Makes sense.
Yes.
and a bit.
Or we say like,
Yeah.
once you
Try
go
to see if we
about
figure out.
just gives a little bit. You are happy, you are really happy with that. That looks like
Yeah.
the
You can use it as a copy, and you can use it.
Esse Mac não tá muito bom. Vou tentar usar assim Docker. Mas tá cheio, mas depois não recorre. Então muito lento.
You actually for me it's showing something like categorical array has no
You should see like,
whatever. Oh, it's still categorical array.
this would be like CSV file. There should be some plots.
We can try to debug later, but I don't know what
There's
happened.
already kind of.
Maybe I updated the notebook preparing like before the weekend. I didn't check this again because I didn't add the answers to the exercise. But I will. We can go later and see what exactly is happening there. It should be something trivial or some dependency that's not in the right version.
How do you do?
If it's
This
no
operator,
data,
Yes.
it's
you say backslash.
But just a notebook.
It is what.
Yeah,
Keep
download
here.
this GitHub repo and then
Okay, so
just open it
it's,
in my.
I'm just gonna put it here.
Yeah,
So
okay.
it's- so it's this one.
Only
And
working
then
Docker, it's just
And
Takes a
then
while.
TO.
small
T
exercise.
O.
Make it
TO.
slow.
Yeah, like the 2 in
Docker
English,
will
and then
always
press
make
tab.
things slower, especially
Yeah,
on Mac.
first an arrow.
I want to,
And
nothing personal.
You gotta draw it.
Yeah.
It's
Yeah.
written
Do
here.
those things
So
slow.
you get the
I'm not sure what I want
combines
to
the
use.
columns into the
Maybe
final.
just using a Jupyter notebook for my presentation Thursday will be
The
fast.
way they do the hashtag
And it's
I don't
loading
know.
up, right? At least
I'm not sure.
Like you would
it's
just
getting,
like this.
now it's the way you kind of
Upload the Docker on top of.
Yeah, yeah, I think so. It would be good just like this.
Mine equals
Add checks.
Yeah, but I stopped trying.
Yeah. Sounds wise.
You also didn't manage to run? How is it?
Well, on a dog, I stopped trying.
Okay, yeah, no, it's I'm not using Docker, but even here it's
Visual
usually it's
Studio.
running, so it's
It's going good. But I had some issues with
I'm just
I
trying
love it when I just said that.
in Visual Studio.
Yeah.
Looks fine.
just doing.
And it's very
So guys, let's finish the first section, right? So just for the last bit, and then we can go for like more questions, right? So this last session here is on the geodata science pattern that's called split, apply, combine. So that's a pretty common pattern that's actually very general, right? So if you learn how to do split, apply, combine, I mean, that's an operation that happens everywhere, like everywhere, every time you need to compute a statistic or you need to
The
process your data in ways to get like quick answers to questions.
Okay.
Like you pose your scientific question and you want to find an answer, it's usually a split, apply, combine. The pre-processing pipelines, they are for like transforming your data in non-trivial ways. But after you get to your final, let's say, data set, you do a split, apply, combine to answer the question, right? So that you pose the question, split, apply, combine to answer. And the idea is that we have this geospatial split, apply, combine, which is made of 3 macros. We call macros in Julia these functions that start with an add sign. And these are, I think in R, the same name, like group by, transform, and combine. And what I'll do here is just show you an example, and then we go at a specific exercise at the end, right? So here, for example, assume that we have loaded the same data set we've been playing before, which has the point set column, right? So we saw that if you loaded the CSV file, it had a geometry column which was made of points. And say that for some reason, these points actually represent hexahedrons. There are 3D geometries, which they actually are. But the way that this industry saves the data, they save as a CSV and they give this as metadata. They say, hey, this is the center of the hexahedron, and the hexahedron has this size. So they go here, say, I want to transform these points into hexahedrons or any other geometry. And for that, I would do a transform operation that takes this geometry column and converts into other types of geometries. So the function that I would do here is just say a function box that takes a point and constructs a box around that point. It's just very simple example here. So you say, take my point, subtract this vector 2, 2, 2, and take my same point and add the vector 2, 2, 2. So I'm saying the point is the center of a box with these 2 corners, right? So that's basically what the function is telling. And what I'll do here is just take my data set and transform. So I'll transform my data set and I'll create a new column, which is not new, right? I'm just transforming an existing column that calls the function box on the column geometry. So I'm taking points and converting into hexahedrons or boxes, right? So here you see that my geometry now is made of, is a column of boxes, right? And the idea of these boxes is that now we have volume, right? So these measurements that are associated with a volume. It's not just a point without measure. It has a finite volume, right? And so this idea of applying functions to columns is super easy to understand, right? But look at the behind the scenes. So we created this blocks data set, and I'm taking the domain of this data set, and you see that it became a geometry set. It was originally a point set. It became a geometry set of boxes, right? And one of the things that we can actually do here is take this transform and use with group by and combine to get very sophisticated geometries, right? So for example, The way that I'm writing here, I'll split it into steps, but just see the big picture here. The big picture is the following. You give me a geospatial data set that I'm calling here blocks, and I'm feeding it into a sequence of macros, right, which are the three types: group by, transform, and combine. The first one, I'll say group my data set by the category geo, which is a categorical variable. And then after I have these groups, I will combine the groups into new variables. So I'll say, give me the mean value of gold in groups and the standard deviation of gold in these groups. So it creates this new geospatial data set where you have the category geo here. There are 1, 2 types of geology. And inside of each geology, it computed the mean value of gold and the standard deviation of gold for geology C1, and the mean and the standard deviation for geology C2. And notice the fancy part here. The geometries became multi-boxes, which means it combined many boxes that are completely random in space. Let's say they're not connected topologically, and created this new geometry called multi-box, which just interprets all these boxes as one thing. And this is very nice because now you can do more geometric processing with this guy. So for example, if I want to compute the volume of the geology C1, I can just say the volume of this geometry, which is very non-trivial, right? So one of the nice things about this is that these are all composable. So let's say, what is happening behind the scenes? So this chain macro comes from the data frames macros idea. I think it was originally written in the, I think it's in the change.jl package, and we just re-export it here. And it just allows you to concatenate expressions without having to repeat the data set all the time. So I'm saying, pass this data set to a sequence of operations. But what is happening behind the scenes is that we are calling one by one. So I say, group by the data set according to the geo column. It creates a geospatial partition, which is, again, lazy, right? So it says there's a view of the data set with 1,700 boxes, and there is another view with 2,000 boxes, which are this geology 1 and geology 2 types. After it has these groups, which have their boxes associated, you can perform the transform on the groups, right? So I say, combine these groups and create these new columns, the mean of the column AU and the standard deviation of the column AU. And so that's what's happening behind the scenes, but it's happening in a way that hides from you all this complexity of grouping geometries, doing more of the geometric processing behind the scenes and letting you concentrate on your data science pipeline, right? So here, for example, is this exercise where we want to compute, let's say, the total mass of gold that will be mined, let's say, from each lithology, and we want to implement this as this sequence here, right? So I'm giving you the recipe on how to compute this number, right? And I'll just give you maybe 1 minute to try this out. I don't know if it's enough. Or maybe I should actually, for the sake of time, just do this and then we can go for questions. I think it's better. So what's the idea here? We posed our question, right? So the question was, what is the total mass of gold that will be mined from each type of lithology? So imagine that you have your satellite image or your coral reef model or volcano model. You want to pose questions like this. What's the mean value of this inside of each type of rock, whatever? To answer this, we'll probably use one of these three macros here. So I would do it here. So first, I'll chain my blocks to start doing things, right? So if I do just this, I think it's not going to do anything because it's just chaining this data set into nothing. So it's just returning the original data set, right? So the first operation is group by. I want to group my geospatial data set into different lithologies, right? So I'll say group by lithology, which is the column of lithologies. See, it created a partition with 4 subsets. So there is 4 sets of boxes that are in space which have different lithology. Now I want to transform to compute the mass of gold because this variable AU is called a grade. It's kind of a percentage of volume. And so to get mass, you have to multiply the density times the percentage times the volume of the block, right? And now it's where it gets interesting because you can say transform and I will create this new variable. I will call it mass, maybe, yeah, mass. That's my new column. And my column will be this multiplication, right? So I have a column of density, which is called rho. I'll just say double column rho, times the column of percentage of gold or grade, right? So say column AU times the volume of the block. And that's where the geometric processing enters, right? So I'll say the volume of the geometry column. And that's going to be the magic of this geospatial split apply combine, because it will understand that the special word geometry refers to the boxes. It will call the volume function from the meshes.jl package, compute volumes of boxes and hexahedrons, whatever, and then return back a geospatial data set with everything as expected, right? So here I'm creating this new column called mass, and it shouldn't change the output because it's still a partition, right? So I'm not seeing, if you want to see the result, you can actually hide the group by, right? So that it just transforms and creates a new column. But to get the final result, you see, you have to combine these masses into the total mass, right? Because you have still the 4 groups. So I'll just take this new column of mass that's inside of each group, and I'll combine into a new column. I'll call it mass again, which is just the sum of the mass. And you see that magically, after some time, it gets to this where you have, for each lithology, a total mass of gold, and this lithology is represented by a multi-box of 2,000 geometries that are of type box. So here, you are actually associating features to groups of geometries, which is super nice. And most nice yet is that you can visualize this as before. So this, I'll show here, let's say, the final answer is the total mass, right? So I can say the mass is the sum of the mined mass. And you should get your answer right. And then you can actually view with our viewer, right? So this is a 3D data set where the geometries are multi-box. And it will show here as easy as if it was a 2D data set. And the geometries that are multi-boxes, they will just show as different colors because these multi-boxes are associated with different values of mass, right? And that's going to take some time because it's running on my tablet, but it should show in a few seconds, hopefully. And in order to get the same visualization, you need to run the notebook geodatascience.jl instead of geodatascience-docker, which is the one that's done with Maki.
Can you scroll up again? Can I just see the solution?
What is it?
Can you scroll up a little bit?
Yeah. Yeah, and as you can see, did you copy here already?
That's fine.
Yeah, I'll come back later. So if you see here, I just asked to view this geospatial data set, and it's a 3D volume where each column here is a subgroup, right? So this is actually not trivial to visualize, right? Because we have multi-boxes, or any multi-geometry from matches will work. It will figure out that all this geometry should plot it in one color. The other geometries here from the other subgroup should be plotted in the other column. But this is done behind the scenes, like hidden from you, right? So that's the idea. At some point we want to be able to do geospatial split, apply, combine, and just view directly in space what the results are. Here are just some additional resources. So if you want to check this in more detail, right, you go to the Geostats documentation. We try to update the docs every now and then. And there are some other related packages like geotables, inmat.jl, and CDS API that allow you to get data into Julia more easily. Here at the end is just a demonstration where you can load a shape file, let's say from a file on disk. And the geotables package is just a package that uses some of those packages that represented this morning, like shapefiles.jl, geos.json, and wraps them up into a single load function that recognizes the file extension and just reports the data set with geometries that are meshes geometries, right? So it just loads the data, converts the geometries to meshes, and shows us a geospatial data set to do whatever you need, right? And the same here, the interaction of the 2D plot, right? So you can zoom in and zoom out, choose the variables that are available in this data set to see. And that's the idea. There are some things that are still working, being developed, right? So it takes some time to get this viewer fully smooth, but that's the idea. And here I think I'll stop for a short break and questions, and so we jump to the second notebook. So let's see. More 10 minutes of questions there. And if you want to try the second one, I think it's going to take even more time to load, so just do it right now here while it's here in the break. So go all the way up to the top, click on the Pluto icon. You can cancel the Geodata Science one, which was running. And then we go to the second one, which is called Geostatistical. This one is going to be taking more time to load, and so it's a good idea to start it up. What is it? Only 10 minutes more? Is it supposed to be 45 plus 15 plus 45? It's like 2 hours to yeah, so it's like 14 to 15 was 1, and then 15 to 55, right? So what time is it now?
Yeah.
Yeah.
So it's 15, 45 already?
Yeah, so.
Wow. Man, I didn't realize it's taking more time because I calculated the timer.
Oh.
So just pass through very quickly the other one if it's time. 10 minutes, right? 10 minutes.
Oh, yeah. Is equal to what?
Okay. First and then
Wait, sorry.
yeah.
So yeah. So guys, actually I think I miscalculated the time of the session, right? So I think I'll just go skim quickly the second one, and you can run it locally later, but we only have 10 minutes left, so that's not going to be enough, but see. The idea of the second one here is just to show some of the machine learning challenges with geospatial data, right? So for some of you who already followed some of the JuliaCon events in the past, I think some of this material is already known. But for you who are seeing for the first time, like the idea is that if you try to do machine learning with geospatial data normally, you encounter many difficulties, right? So this machine learning theory and methods and tools that were created for table types which are not necessarily under the same assumptions of geospatial data sets. For example, your samples are not IID, your samples are associated with specific volumes, or we call support. And there are many challenges, for example, data set shift, right? So if you train your model in one place and apply in another place, things just don't work because the distributions are different, right? So this notebook here that you have access to read more carefully later just goes over some of these challenges, right? I don't know if it's going to be enough time to see all the examples running here, but the idea is that there are challenges with both, let's say, classification, regression, or any of these traditional machine learning workflows. And what we propose here is that there are ways of formulating the problem differently that take into account the fact that these data have domain associated with them and that the samples are georeferenced, right? And in this notebook here, which I don't think will be loaded in time, it shows like what can happen if you don't take that into account. But it's basically showing that if you run a classification model on a satellite image, for example, and you try to make an estimation of the error of the model in another different area, your estimates of error will be super optimistic. It will show like, oh, you have, I don't know, 10% error. And then when you actually deploy the model in the field, you get like 20% error or more. And that's happening for a very good reason. And this notebook explains a bit of this literature and shows that there are ways of estimating this error that don't fall into this, the problems, right? So there are some literatures and references we can go over the week together if you have interest in that. But the idea is that the Geostats framework integrates with a bunch of existing stacks like MLJ in Julia, which is the default, let's say, stack for machine learning, and it does some layers of abstraction to, let's say, avoid some of these issues, right? So there's still things being worked on, but there are, this is the code, how it looks like more or less. So you define for example, that you want to make a classification based on some bands of a satellite and you want to predict the crop variable, you define your learning problem where you have a geospatial data set as the source, a geospatial data set as the target, and you have your learning task, T. You load a model, let's say that's traditional, let's say a decision tree classifier or something, and you wrap this model into a solver. We call this solver here the naive pointwise learn solver, right? You can then create what we call these validation procedures, like block validation, leave ball out. These are specific to geospatial data sets, to estimate a value for this error that's more, let's say, close to the actual error you get from the model, right? There are references that you can follow here, but I don't think, let's see here how the visualizations are going. So this here is the data set. You have like a place of the image which has labels, and you want to predict the crop type in the other part here. And all these plots are interactive after the notebook are loaded, right? So you can zoom in and zoom out to see more. And at the end here, I also show, for example, how clustering also can be very problematic if you don't take into account geospatial coordinates, right? So you compare, for example, k-means with something more geospatial, and you have more control of the final clusters you get if you use these geospatial clustering methods instead. There is a paper, which is the paper we published on this matter, right? So we introduced this geostatistical learning framework and formulation that you can read in more detail. It's more mathy, but it's available open access. And here's the example that I would like to actually see, but I don't think we'll have time, but it's actually showing how you can load a 3D mesh of a building. It's like a 3D model where you can train a model in a specific part of the building and predict the variable you want in another part of the building. So it's very advanced in the sense that you can split, apply, combine pieces of the building, which is very cool. So you get these complicated geometries like hexahedrons, triangles, whatever. You can split these geometries, transform and combine, and things will still work as if it were an image or a point set. It's very non-trivial to get this working. But it's going to take a lot to compile. So I'll just finish here, wrap up, and feel free to load the notebook later and then we can chat. So I think with that I'll close the session in the sake of time, right, John? We don't have much more.
Yeah, unfortunately not, but thank you very much. It was very interesting. And I highly recommend that you check this second notebook because it's, first it has very interesting stuff, it's very well explained as well. And it has all the references, etc. So it's a super job.